let's finish up. If we can get this done in one more video. Section 1.5, normality, quotient groups, and so forth. Let's quickly recall, since this will play a big role in the next result, the canonical epimorphism. Pi was a mapping from group G to the quotient group G mod n, defined as pi of a equals an. So we're simply mapping an element of G to a left coset of the quotient group G mod n, or right coset. We wouldn't be talking quotient groups unless n was a normal subgroup. And if n's a normal subgroup, one of the many things we know is that left and right cosets coincide. So it doesn't matter whether we pick a left or a right coset, the sets are the same. We'll write this up in left coset notation. It doesn't matter when we're dealing with normal subgroups. But that's the canonical epimorphism. And we prove this kind of lengthy result, theorem 1.5.6. Let's do a quick synopsis of that with some particular observations to see how we're about to use it. If F maps G into H is a group homomorphism, and N is a normal subgroup of G contained in the kernel of F, okay, so we've got a normal subgroup, certain placement of it, then there's a unique homomorphism, F bar, mapping the quotient group G mod N into H with some other conditions satisfied. And here's how we'll use it. F bar is an isomorphism if and only if F is an epimorphism and N is the kernel of F. So what this gives us is F bar is an isomorphism between the quotient group G mod the kernel of F and with whatever we get on the right-hand side, provided we have the ontoness, the surjectivity. Well, F bar is onto its image. So if we replace H with the image of F bar, and we take N to be the kernel of F, then we've got an isomorphism. That's part of the claim that we have from theorem 1.5.6. We talked about it in terms of diagrams. And that's exactly what the first isomorphism theorem is. So the proof of the first isomorphism theorem, way easy given that previous result. Says if F maps G into H as a homomorphism of groups, then F induces an isomorphism of G mod the kernel of F with the image of F. Okay, that's exactly what we had in theorem 1.5.6 when we took in that normal subgroup of G to be the kernel of F, and we made sure we had the ontoness, the surjectivity. Well, every homomorphism is onto its image. All right, we'd throw away the stuff that's not contained in the image, and of course you got something that's onto. So this follows immediately from theorem 1.5.6. To establish F bar as an isomorphism between G mod N, where N is the kernel of F and the image of F. Maybe quick passing observation. Yeah, remember the kernel of a homomorphism is a normal subgroup, as we proved somewhere along the lines. So by taking the kernel of F as this N subgroup, it really is a normal subgroup, and so the quotient group exists. So this story with these isomorphism theorems, it will state three of these. The other three won't be quite this brief. They relate groups and quotient groups in the crudest of senses. This is material also covered in the Fraley book. It's in, I guess it's like section 34 of the Fraley book. It's in the advanced group theory part of that senior level book. The first isomorphism theorem, along with the theorem 1.5.6 on which it's so heavily based, this is fundamental stuff in modern algebra. It relates quotient groups, which have cosets as their elements, to a group homomorphism in its kernel. In fact, things are developed, as I've mentioned, in a kind of a different order in the Fraley book, in the senior level modern algebra book that I like so much. I've got a diagram here to kind of illustrate where F and F bar are, where the quotient group is, where the elements of group G are. And we get the following image. It might remind you, if you're familiar, of the ETSU Abstract Algebra Club logo, which I happen to have on my hat. It's a little bit different. The logo was designed around Fraley's presentation of this material, and this is a little bitty bit different. But what we have here is group G. So here are all the elements of group G in these little blobs. The little blobs are cosets. Here's homomorphism F. F maps the elements of group G down here into some other group. This is happening in group H in the notation of what we had in the past. If you like, I've just drawn the part of H that's the image of F. I might have additional things out there somewhere. But F maps group G into group H, and here's the image of G under F. So that part of H containing the image. The blobs, the blue one here, represents the kernel of homomorphism F. Right, we've got the identity down here in group H, E sub H, if you like, E prime, the identity down there in that other group, the codomain of homomorphism F. So everything mapped to the identity down here, that's in the kernel of that homomorphism. Let's call it K for kernel. You know, the kernel of a homomorphism is a normal subgroup. So we can take left cosets, and they will coincide with right cosets of that normal subgroup K. So we produce these colored blobs, and these colored blobs represent cosets of K. Left cosets, right cosets. K is a normal subgroup. They're the same. Now, something implied by this, I think this is a useful image, is F ain't one-to-one unless these cosets are simply individual elements of G. F is many-to-one, and it is, if you will, it's the same number to one. Remember, all these cosets have the same cardinality, if you will, like the same number of elements with some caveats about infinities. But all the blobs here, they're the same size. So F takes this blob to the identity. F takes this blob to this element of H. And the two blobs are the same size. If each of the blobs contained 10 things, 10 elements of G, then F would be a 10-to-1 function versus a 1-to-1 function. It's a many-to-one, and the many is the same because each of these cosets, as you know, have the same cardinality. We showed that in the previous section. Now, the F bar was produced by a composition of, we had a diagram that indicated that back here. F bar could be thought of, F can be thought of as, how's our diagram commute here? It's F can be thought of as the canonical epimorphism pi followed by F bar. So see if we can get that part out of the picture. Okay, F bar mapped the cosets of K and G, in the kernel in this case, map those cosets down here into group H onto the image of F or the image of F bar. And what we're saying is, if I'll take first pi, the canonical epimorphism, and follow it with F bar, we'll get the same behavior we get from F itself. For example, let's take this coset containing element A. The canonical epimorphism, if you take any one of these elements of this coset, pi will map you to, say, the left coset AK. This second element is alpha instead of A. Well, the left coset alpha K will be the same as the left coset AK. Doesn't matter which of these things you pick, we always get the same coset out. So the canonical epimorphism will produce from any of these the same left coset. Now F bar is going to take that and take it down here into group H, and produce output F of A. So what homomorphism F does, if I look at this point here, homomorphism F maps this point because it's in the coset containing A, maps it to F of A. The composition, first pi, then F bar, would take this element, associate it with this coset, and then F bar would take that coset AK and map it to F of A. So that's how homomorphism F relates to the canonical epimorphism and this mapping F bar that we've introduced. Okay, I can't draw a lot of pictures in algebra, but I like that one. All right, we've got a corollary followed by the second isomorphism theorem. This is kind of like the last two results we had. This 1.5.8 is actually fairly lengthy. The isomorphism that will follow from it is relatively brief. Maybe not as brief as the first isomorphism theorem, but let's look at 1.5.8. Oops, 1.5.8, and go through a proof of that. Okay, claim here is if F maps G into H is a group homomorphism, N's a normal subgroup of G, M is a normal subgroup of H, and F of N is a subgroup of M, then F induces a homomorphism, F bar, mapping the quotient group G mod N into the quotient group H mod M, given by, let's see, elements of G mod N would be, say, left cosets of N and G, and they're mapped to, say, left cosets of M in H. So saying we take the left coset AN and map it to the left coset F of AN, that's the right structure. It takes in the right kind of thing. G mod N contains left cosets of N and gives out the right kind of thing. Over here, we'd get a left coset of M and H, and that would look something like this. The F of A would have to come from H. Of course it does. F gives us out things in H. Some observations, a little bit more on what's where. N's a normal subgroup of G. Okay, so that's kind of domain type stuff. M is a normal subgroup of H. That's happening over here in the codomain. Saying N is a normal subgroup of G means G mod N, that quotient group is defined. Saying M, or hypothesizing M is a normal subgroup of H, is implying that H mod M, that quotient group also exists. So the normality conditions are necessary for us simply to talk about the quotient groups. And we've got this added condition that F of N is a subgroup of M. So the subgroup of G is mapped by F. The subgroup N of G is mapped by F into subgroup M of H. So there's a relationship between those subgroups and the mapping. So first claim induces a homomorphism between these two quotient groups here. F is an isomorphism, next claim, if and only if the join of the image of F with M actually equals H. Makes sense, at least setting wise. The image of F is in the right place. It's over here inside H. M is a subgroup of H. So yeah, all this stuff is happening inside subgroup H. I stopped mid-sentence here. Let's see, F is an isomorphism if and only if the join of the image of F with M equals H, and the inverse image of M is a subset of N. Inverse image, right? We're not assuming H is one-to-one and onto. Apparently, it looks like we're establishing that somewhere in here. But I can always talk about inverse images, whether I have bijections or not. So the inverse image of M is a subset of N. Yeah, let's see. M subgroup of H, N subgroup of G, the mapping of the homomorphism, inverse image of something in H, like M, would be something in G, like N. So the setting makes sense. In particular, if F is an epimorphism such that f of n equals m and the kernel of F is a subset of n, then F bar is an isomorphism. We're in the middle of proving 3 isomorphism theorems, so this last observation is pretty relevant to the future stuff. Okay, so let's go through. I don't consider the following terribly elegant. We'll break it into 3 pieces. We'll actually leave the second piece dealing with this join stuff. We'll leave that as a homework problem, if you will. But first, let's consider the claim. F induces a homomorphism, F bar. All right, so let pi map H into the quotient group H mod M be the canonical epimorphism. So that maps an element of group H into a left coset of M in H. Definition. Consider the composition, pi composed with F, which will take G into H mod M. Let's see, F will take G into H, and then pi will take H into the quotient group. So yeah, the composition, first function, second function, think of these acting on something on the right. So you actually read it from right to left in terms of orders of what happens. F first takes G into H, and then pi takes H into this quotient group H mod M. So the mapping makes sense. We're working under hypotheses of normal subgroup, and this subgroup containment. F of n is a subgroup of n. So F of n is a subgroup of n, that's hypotheses. Then n is a subset of the inverse image of m. Yeah, all of n is mapped into m. There might be some other stuff mapped into m as well. So all I know is the inverse image of m. So we're back in group G when I talk inverse images. The inverse image of m is a set that contains n. Inverse images of groups under homomorphisms are also groups. We'll recall that here shortly. So it's actually a subgroup relationship. The kernel of pi f, okay, kernel is a stuff mapped to the identity. So the kernel of pi f consists of all elements of G mapped to M under the composition. That is, the elements of G mapped to M by F. All right, let's dissect that a little bit. Pi f deals with a mapping into H, followed by a mapping into the quotient group. So ultimately, we're getting the codomain to be H mod M. What's the identity in the quotient group H mod M? It's if you will, that denominator group. The identity in quotient groups is always the denominator group, the M in this case. So this quotient group consists of cosets of M in H, and the identity in that group of cosets is M itself. So kernel of pi f would be the stuff that's mapped into coset M. So pi f would map us into M under the composition. If we look at how the canonical epimorphism maps things, pi of h equals hm, we get pi of h equals hm. When does that equal m? When is hm equal to m? Well, that occurs if and only if h itself is in M. So some properties we've seen along the way dealing with cosets. So ultimately, then the kernel of the composition pi f, not drawing the composition symbol all the time. This is standard notation from Hungerford. I'm a little more comfortable with a little circle for composition. But anywho, the kernel of this mapping consists of things that are mapped to M by F. The things that are mapped to M by F, those things, the things live in G, would be the inverse image of M under F. So F inverse image of M. This is the stuff that's mapped by F into M. And so this is the stuff under the composition that's mapped to the identity. That is, that's the kernel of the composition pi F. N is a subset of the inverse image of M. We had that up here. We just argued that the inverse image of M is the kernel of pi F. So we've got N is contained in the kernel of pi F. The kernel of a mapping is a normal subgroup. We've got a subgroup of the kernel. So N itself is a normal subgroup of G contained in the kernel of pi F. Let's see, I guess we had the N as a normal subgroup of G. We actually had that as hypotheses, didn't we? So we've got N's a normal subgroup by hypothesis, and it's contained in the kernel of pi F, as we just showed. So let's see, is that the first claim? Not yet. Theorem 1.5.6 dealt with such mappings. So we'll apply theorem 1.5.6 to the mapping pi F. This would be denoted with the overline, with the pi F bar as the notation we had in theorem 1.5.6. And we get this mapping of the quotient groups given by taking A to the function evaluated at A. The projection here producing a left coset. So we're taking AN and we're mapping it to function pi F of A. That would be pi of F of A. There's F of A. Pi, the canonical epimorphism, turns the F of A into a left coset. So the function composition is spelled out, actually spelled out in detail in the next line. So theorem 1.5.6 gives us the existence of this homomorphism. In fact, we weren't addressing uniqueness here, but theorem 1.56 gave us that there's a unique homomorphism that behaves like that. And theorem 1.5.6 told us this thing is an isomorphism if and only if pi F is an epimorphism and the kernel is subgroup N. So getting a lot of mileage out of theorem 1.5.6 still. So there's still a corollary of that. But that's the conditions we had here. F induces a homomorphism. Let's see, given by this. So we've got a homomorphism. Yeah, we're not claiming this stuff about the kernel just yet. All we claim was the existence of a homomorphism in the first part. So a little extra stuff here. Also true by theorem 1.5.6. Exists a homomorphism, and here's some properties of it we know by theorem 1.5.6. Now the next part deals with the join of the image of F with M and the inverse image of M and its location. This last condition, this pi F is an epimorphism and N equals a kernel, we claim that's equivalent to these two conditions here. So now we're using this information that we've got an isomorphism if and only if these two conditions apply. The claim is those conditions are equivalent to the join of these two things is H and the inverse image of M is a subset of N. We're leaving as homework. We're still going to use it in the proof of the third part. So that takes care of the first claim. Theorem 1.5.6 does the heavy lifting for that. The claim about an isomorphism in terms of joins, we leave as an exercise. The in particular part. So now we need to deal with the in particular part. In particular, F is an epimorphism such that F of N equals M and the kernel of F is a subset of N. Then F bar is an isomorphism. So another claim of isomorphism here. If F is an epimorphism such that F of N equals M. So there's our hypotheses. And the kernel of F is a subset of N. Then we want to draw the conclusion of F bar being an isomorphism. If F is an epimorphism, and on to homomorphism. Then being onto, being surjective, the image of F and H are the same. Remember, F mapped G onto H. If F is surjective onto, then the image is H itself. The image of F is the image of F, join M. The image of F is all of H. We join it with some more stuff. Remember, M is a subset of H, normal subgroup of H, if you like. So by taking all of H and then joining this stuff here, you're not picking up anything new. So trivially, we get this little equality between the image of F and the image of F join M. We're trying to use this exercise stuff that we had in the second part. We're hypothesizing F of n equals M. Hypothesizing F of n equals M, and the kernel of F is a subset of n. We claim gives the inverse image of M as a subset of n. Suppose not. Suppose there's something in the inverse image of M that's not in n. That is, suppose F of G is in M for some G not in capital N. So we're violating this. We found something else in the inverse image that's not in N. That something is G. F of G is in M, but G is not in N, capital N. Here we're hypothesizing F of N equals M. So for some little lowercase n and subgroup capital N, we do have F of N equals that element of G. I'm sorry, that element of M, F of G. So we get the existence of a lowercase n, such that F of N equals F of G. We do know that F of capital N equals all of M, and F of G is something in M. So there's something in capital N, call it lowercase n, that's mapped to that element of capital M. So let's take this equality and run with it, and the fact that F is a homomorphism. F of Gn inverse, let's consider this, homomorphism properties, tells us that's F of G times F of N inverse. Homomorphism applied to inverse images is inverse images of, inverse elements of images. So F of N inverse is F of N inverse. Homomorphism properties established earlier. F of N and F of G are the same, so we can replace that with F of G. Now we get F of G times F of G inverse. Well, that's the identity. So we've got F of G in inverse is the identity. By the way, that's the identity in the rightmost group. Right? It's clear from context. It's implied by the context at least. But we do have F mapping us into H. This is F of something, so this is the identity in H. Just keep an eye on that stuff. So we've got G in inverse in the kernel of F. G in inverse is mapped to the identity. That's what the kernel consists of. We've assumed as well that the kernel is a subset of N in this setting. So we can take G in inverse. Let's multiply that element by lowercase n. G in inverse is in N. Lowercase n itself is in N. So the product is in N. G in inverse times lowercase n. The n's cancel, leaving us with a G. And this shows that G is in N. This is in capital N. That's in capital N. So G itself is in capital N. Contradiction. G was chosen outside of capital N, somewhere else in G. So we can draw this conclusion, this subset inclusion we just established by contradiction, that the inverse image of M must be a subset of capital N. So now we have the conditions of part B satisfied, the homework part. We have the image of F join M equals H. Yeah, that we had fairly trivially. And we've got the inverse image of M as a subset of N. We've established that. That's equivalent to my part B, F being an isomorphism. In this case, we've established it actually for F bar. So we get F bar is an isomorphism. It's some of the notation of the previous stuff. And we've shown F is an epimorphism, F bar is an isomorphism. Definitely, I guess I got to go to theorem, what was it, 6 to get the details on the F bar. But we draw the conclusion of an isomorphism. That establishes the third part. Let's go back to the notes. I think it follows immediately on the heels. Let's look at the second isomorphism theorem. So theorem 1.5.6 was kind of involved. Theorem corollary 1.5.8 is kind of involved. The isomorphism theorems themselves are not quite as weird. Second isomorphism theorem says, if K and N are subgroups of group G with N normal in G, then K mod N intersect K is isomorphic to NK mod N. Let's look at a proof of that and make some preliminary comments. We've seen in the past that if N is a normal subgroup of G and K is a subgroup of G, then N times K, this really is a group. So we know this is a group. N is normal in G. Well, then N is normal in this subgroup of G. That's the easy part with normal subgroups. Intersection of two subgroups is a subgroup. So this is really a subgroup. We've got the normality of N, giving us normality of N intersect K. So we do actually have a normal subgroup. With this intersection, we've got a subgroup of a normal subgroup. And so this quotient group K mod N intersect K is meaningful, and we're going to go through and establish, primarily using the first isomorphism theorem, this isomorphism claim here. Okay, maybe we still have some details to mop up. N is a normal subgroup of NK, so that was given by theorem 1.5.3, part 2. NK, the join of N and K, is also a group. That was theorem 1.5.3, part 3. So we went through and looked at joins and subgroups for these NK things with exactly the same hypotheses that we have here. All right, so we need a mapping first. Let 1 sub G be the identity on group G. Consider the composition. Okay, this is mostly paperwork, this introduction of an identity function. We're taking set K with the identity mapping, mapping it to set NK. Well, now everything in K is in set NK, but we're doing this kind of embedding so we can use a particular kind of canonical epimorphism. So take K, embed it in NK, there's a bunch of stuff in N times K, certainly K itself, all those elements are in subgroup NK. And then use the canonical epimorphism to take NK and map it to the quotient group NK mod N. So the whole purpose of introducing this identity was so we could use this canonical epimorphism. We wanted to talk about this quotient group, right? So it's the right-hand side of the alleged isomorphism equation. So introduce the identity, giving us this kind of mapping here. This is a homomorphism. The identity is certainly a homomorphism. Canonical epimorphism is a homomorphism. So the composition, pi composed with the identity, 1 sub G, is also a homomorphism. Compositions of homomorphisms are homomorphisms. The identity 1 sub G comes first, and then the canonical epimorphism, right? So the composition is written in the correct order. The 1 sub G comes first, and the canonical epimorphism comes second. So yeah, they're different in the diagram here from the order given here, but all that's the way we deal with the notation. The kernel of F is the elements of K, right? F maps K over here. So it'll be the elements of K mapped to the identity in this quotient group. The identity in that quotient group is capital N. So we're looking for elements of K that under F are mapped to capital N. Capital N's the identity, so that's what kernel elements are, things that are mapped by F to the identity of whatever we have over here. Over here, we've got a quotient group, the identity of which is capital N. Certainly, everything in N itself, if N and K overlap, they have to. They share the identity if nothing else. But if N and K overlap, an element of N would be embedded in here and then associated with, say, a left coset of capital N with respect to that element of capital N, and that would just produce capital N itself. So under this mapping, everything in N is definitely in the kernel of F. But we're interested in the elements of K that behave like that, and that's exactly the elements that will lie in N. So we're interested in the elements of K that are also in N. I'm interested in elements of K because the mapping goes from K to this quotient group. The homomorphism F goes from this K to this quotient group. So the kernel of that homomorphism would be the elements of K that are also in N, because that's the ones that will be mapped to capital N under this little scheme, identity and then pi. So first isomorphism says F induces an isomorphism between this group, K, mod the kernel of the homomorphism. The kernel we just showed was N intersect K. So we've got an isomorphism between K mod K intersect N with the image of that homomorphism. So what we just exactly saw in the first isomorphism theorem. So we've got K mod K intersect N isomorphic to the image of F. That's the left-hand side. Okay, so the image of F is isomorphic to this left-hand side, is what we've shown here. We're going to quote this here in a couple of lines. Let's give it a name, asterisk. Now, about the right-hand side, Nk mod N, every element of Nk mod N is of the form element of the group Nk, capital N, capital K, so that would be a lowercase n, lowercase k, times capital N. A left coset of N in Nk is always of this form. Now, N is a normal subgroup of G. So, Nk, think of this as a, let's see, a right coset of capital N by element K, this element K that arose up here. So here we've got an element of the right coset, capital Nk. Well, the right coset, capital Nk, is the same as a left coset K, capital N. Capital Nk equals K, capital N. Those cosets are equal. This is an element of capital Nk, so it's also an element of K, capital N. Say it's K times N sub 1 for some N sub 1 in capital N. Going all the way back to the definition of normal coset, I guess, which we had, I don't know, several pieces, but this is one of the pieces. Left and right cosets are the same. We're just dealing with elements of a left coset and a right coset. So we've got the equality Nk equals K N sub 1 for some N sub 1 in capital N, whence Nk times N, this left coset of N, make that substitution, Kn1 equals Nk, equals this left coset of capital N. Oh, but you know what's going to happen next. Little n sub 1, lowercase n sub 1, is an element of capital N. So we can absorb that, as we've done in the past several times. We can absorb that n sub 1 into that subgroup capital N and simply write this as K times capital N. So the n sub 1 gets absorbed as before. K capital N. Why? That's what mapping F does. When mapping F takes in an element of K and gives out a coset of N, a left coset, say, based on that element of K. That is, F of K is the left coset K capital N. So we're getting an f of k out here. This was started by choosing an arbitrary element of this quotient group, and we've shown that that arbitrary element of the quotient group, this left coset, in k times capital N, is f of something. It's f of k. So we took an arbitrary thing over here and showed under mapping f, it's the image of something over here. So every element of nk mod n, every element over here, is the image of something over here. So everything over there is in the image of f. So f is onto. And it maps us into this set. In fact, we just demonstrated it maps us onto this set. So we've got an onto homomorphism. So f is an epimorphism. The image of f is nk mod n. There's the image in the story again up here by asterisk. We had that the image was isomorphic to this quotient group. Well, this is the image, the other side of the equation in the theorem. So we get from asterisk that k mod k intersect n is isomorphic to nk mod n because they're both equal to the image. We picked up an isomorphism along the way. Yeah, these are structurally the same. They're not equal. The elements on the right-hand side here are, say, left cosets of capital N in this group. And over here, the elements are, say, left cosets of N intersect K in K. So they're different things, but the structure is the same. They're isomorphic groups. Back to the notes. Okay, let's look at an example. Let's go through this, maybe not in great detail. This is actually an exercise out of Fraley's book. And let's pick a group G and two subgroups, K and N, and let's illustrate the second isomorphism theorem. In particular, let's see how these elements of this quotient group are mapped to those elements of that quotient group. So let G, say, be integers mod 36. Let K consist of the subgroup generated by the equivalence class 6 bar. Let N be the subgroup generated by the equivalence class 9 bar. Quick observation, and everything in sight's a normal subgroup here because we're dealing with an abelian group. So the normality stuff isn't an issue, but just for the sake of illustration, let's list all the elements in Kn. Okay, an additive example should denote that K plus N instead of K times N because we're dealing with an additive example. It's just notation. And K intersect N. Well, first off, K is a group generated by 6 bar. So we just take 6 plus 6, 6 plus 6 plus 6. Just keep adding sixes until you return to where you started. That's how we find the order of an element. Everything's finite here, so we're good. So we get 6 bar, 12 bar, 18 bar, 24 bar, 30 bar, 36 bar, which is the same as 0 bar, and then we wrap around. 9 bar, 9 bar, 18 bar, 27 bar, 36 bar, which is the same as 0 bar. We're working mod 36, and we've wrapped around. So here's what we get for the elements of K. Here's what we get for the elements of N. Add all possible elements of K to all possible elements of N to get K plus N. We could add 6 bar. What would that produce? 6 bar, 15 bar, there's something new that's in neither of them. 24 bar, 33 bar, there's something new that's in neither of them, and so forth. So you actually pick up some new stuff. We picked up, what was it, 15 bar and 33 bar by adding 6 bar to these. You'll pick up 3 bar. Where does 3 bar come from? How about adding 12 bar to 27 bar? That'll give us 39 bar, which is the same as 3 bar, mod 36. So grind through the arithmetic. You'll produce K plus N is given by these elements. K intersect N is given by these elements. To further hammer home the idea of what a coset is, because I don't think this is really very terribly tangible. Let's look at Kn mod n. Okay, that'd be K plus n mod n in the current notation, in the additive notation. Why, here's K plus n right here. So we want to take cosets of n. Here's n. It's this group generated by 9 bar. So we'll take n and add to it all these things here. Well, they're getting things that are 0 mod 9 in n. If I'll take n and add 0 bar, we'll get the same set of elements as we get when we take n and add 9 bar, or for that matter, 18 bar and 27 bar. All these things are congruent mod 9. All these representatives of these equivalence classes, if you like, are all numbers that are 0 mod 9. So by adding either 0 or 9 or 18 or 27 bar, you produce the same set. So you simply produce n itself as predicted. Right? That's the only time you get n. If we'll go through, we get a similar behavior. If we add 3 bar, we'll get the same as adding 12 bar, 21 bar, and 30 bar. So here's the single coset that results from these 4 different additions. N plus 6 bar, guess what? It's the same as n plus 15 bar, and n plus 24 bar, and n plus 33 bar, because those are all congruent mod 9. And that produces this coset. So we ended up with 3 cosets here. So Kn mod n has these 3 cosets. Let's look at K mod K intersect n. All right, K intersect n consisted of 0 bar and 18 bar. To that, we will add elements of K, which would be these 0 bar through 30 bar, things that are 0 mod 6. Performing the arithmetic, like I said, I want to go through this, not in great detail. The notes are posted online. We'll produce these 3 cosets, 0 bar, 18 bar, why, there's K intersect n itself, 6 bar, 24 bar, 12 bar, and 30 bar. So we get these 3 cosets. How y'all doing? We had 3 cosets there, and we got 3 cosets here. So that's a good sign. It's the same number of cosets in both. Now we wanted to illustrate how these things correspond. How is it that F bar, that isomorphism, is established? Well, F bar takes K mod K intersect n to K plus n mod n. That's the mapping. It's defined pointwise as given here. If we'll go through and see how these mappings occur, then there's all the arithmetic, there's lots of equality, there's mod 6 or mod 18 stuff that's going on. And what we ultimately produce is a mapping of the 3 cosets, 0 bar, 18 bar, 6 bar, 24 bar, 12 bar, 30 bar, to the others, produces this. So 0 bar, 18 bar is mapped to 0 bar, 9 bar, 18 bar, 27 bar. Hey, these elements over here, they're in this equivalence class as well, along with a couple of other things. And that's the pattern throughout. 6 bar, 24 bar, there's 6 bar, 24 bar, and there's a couple of other things. And the new things, in a sense, they always differ by 9, in some sense, from the representatives given here. 12 bar, 30 bar, 12 bar, 30 bar, 12 bar minus 9 bars, 3 bar, plus 9 bars, 21 bars. So some kind of mod 9 thing going on here, as is not terribly surprising. But there's the type of mapping given by the second isomorphism theorem. Let's look at, prove, and then give a maybe even quicker version of an example of the third isomorphism theorem. Okay, of these isomorphism theorems, it's kind of the easiest one to remember in my opinion. Statement is, let's actually go straight to the proof. Statement is, if H and K are normal subgroups of group G, such that K is a subgroup of H, then H mod K is a normal subgroup of G mod K, and G mod K mod H mod K is isomorphic to G mod H. Well, the way to remember it is I think of these quotient groups as just straight up division. And then it's the K's are in corresponding positions like the K's cancel. So I'm not saying that's what it is, but that's a way to remember the third isomorphism theorem. So this one's maybe the least surprising. It's easiest to remember, maybe. Now the elements here, this is one reason I want to do an example. Here, we're taking cosets of H mod K in G mod K. So H mod K is itself a group of cosets of K and H. Yeah, G mod K, these things are cosets as well, cosets of K and G. So we'll be, in the example, we'll do things in integers, mod, whatever. We'll be taking cosets of K and G and adding them to cosets of K, adding them to this particular group, this subgroup of G mod K. So we'll have cosets added to subgroups versus elements added to subgroups. The elements of the numerator group, if you will, the elements up here, that they are cosets. And this is a group of cosets as well. There are going to be a lot of sets floating around in this. Now for the proof, I think it's only one slide long. First, the identity map. Once G maps G into itself, satisfies, it takes K to K, which is a subgroup of H. Define I of G mod K mapped into G mod H as I of AK equals AH. So here we're taking left coset of K and G, AK, and mapping it to left coset of H and G simply as AH. So it's a pretty naive approach. So if it works, all's the better. I is a homomorphism. Yeah, why is that? When I deal with a binary operation in this group, we're going to add cosets together using representatives, or multiply cosets together using representatives. And you do the same type of multiplication over here. Coset multiplication is done by representatives in both settings, both G mod K and G mod H. So you got yourself a homomorphism, an elementary exercise to establish this really is a homomorphism. It's also onto, since each coset of H is in the image of I, yeah, we're going to let A range over all of G. As A ranges over all of G, we look at all of these cosets, we'll produce all of these cosets over here. So we've got onto homomorphism. This mapping I is an epimorphism. Notice what we're looking at here. We're mapping G mod K to G mod H, and looks like we wanted to have a conversation. G mod K, there's a G mod K, and there's a G mod H part on the other side. So I still haven't drugged the H mod K into the conversation. H equals I of AK if and only if A is in H, because I of AK is AH. AH equals H if and only if A is in H. So that's the reasoning for that. Write out what I of AK is. It's AH. And that reduces to H itself, you know, when H can absorb the A, and it can do that when and only when A is an element of H. So that's the claim there. So if we want the kernel of I, we talk about kernels, we can use the first isomorphism theorem. Actually, the first and second, second and third isomorphisms have both depended on the first isomorphism theorem, which really means a dependence on that theorem 1.5.6, I think it was, that we did at the end of the last video. So the kernel of I would be all AK such that A is an H, right? We'd want things mapped to H. So we take these cosets under I would be mapped to H if A is in H. So there's the A is in H, and there's the cosets that I acts on. Domain of I is cosets of this form. So this is what we would get for the kernel. Remember the identity in, where are we going? Here we go. The identity in this quotient group is what? Coset H. The identity in this quotient group is coset subgroup K. So the denominator is always the identity in these quotient groups. Don't tell anybody I said denominators. I don't think that's professional verbiage, but that thing in the bottom there, that's the identity in this quotient group. So H is the identity in G mod H, and that's why we're considering this. So we get something in the kernel of I if and only if we're getting these A's to be chosen from H. And I takes in left cosets of this form. So what we're doing then in this set, the kernel's represented by this set, is we're letting A range over H, and we're taking left cosets of K of the form AK, where A is an element of H. So we're getting all left cosets of K in H. Hey, all left cosets of K and H, that's the elements of the quotient group H mod K. So kernel of I is H mod K. Now we drug H mod K into the conversation, and we've done it, damn it, in a denominator up here, which is very useful for the first isomorphism theorem. H mod K, then we've got is the homomorphism. Theorem 1.5.5 tells us H mod K is a normal subgroup of G mod K. Yeah, kernels of homomorphisms are normal subgroups is what that's about. So we really do have a normal subgroup here. So we really can take a quotient group of this mod that, G mod H mod HK, mod HK. So this quotient, this quotient group really is defined. We really do have a normal subgroup. And the first isomorphism theorem says G mod H, that's the image of I, where did we establish that? Onto image of I includes all of G mod H. We've established that I is an onto mapping up here. So G mod H is the image of I. We know the image of a homomorphism is isomorphic to quotient group mod kernel of that homomorphism. So we get the G mod K, right? We hit the domain over here of the homomorphism mod the kernel of the homomorphism. And we just showed the kernel of the homomorphism is H mod K. Take the kernel of I, kernel of homomorphism I, replace it with H mod K. That pops up over here. Here's the first isomorphism theorem. Image of I is isomorphic to, how about this one? Domain of homomorphism, mod kernel of homomorphism. And the kernel of the homomorphism was that other quotient group. So there's a proof of the third isomorphism theorem. Again, none of the proofs of the isomorphism theorems themselves were very complicated, but they were based on some pretty involved stuff. Back to the notes. Let's briefly illustrate that. Suppose G is the group Z24. H is the subgroup generated by the equivalence class containing 4 bar. K is a subgroup generated by H bar. List the cosets of G mod H. Okay, H is going to have 6 things in it. Here it is. So every one of those cosets will have 6 things in them. How many cosets will there be? There have to be 4 of them. 4 times 6 is 24. Remember, all the cosets are the same size. And here's the arithmetic that produces those 4 cosets. So there's the 4 cosets. Of course, they're produced in more than one way. cosets of G and K, G mod K, sorry. G mod K, cosets of K and G. Let's see, K has 3 elements, so there'll be 8 cosets of these. And let's not get into the arithmetic. Here's 4 of them. Here's 4 more. So there's your 8 cosets of K and G. Cosets of K and H, H mod K. Let's see, let's count them real quick. H is of order 6, K is of order 3. There should be 2. Yeah, 2 cosets of K and H. And there's the arithmetic that produces them, and there's the cosets. Okay, now it gets a little more interesting. Cosets of G mod K, mod, H mod K, cosets of H mod K in G mod K. Okay, again, let's gloss over the arithmetic. Let's just look at the format of them. What you get is sets of sets. Yeah, it's because we got a quotient group of quotient groups. So we're getting sets of cosets is what it amounts to. In these, it looks like we're producing this one, a second one, third one, and a fourth one. I think we got 4 of those, but there's sets of sets, and there's the arithmetic that produces them. Notice you're adding a coset to a set of cosets. Which makes sense. This is a coset chosen from one group, and then we're looking at that that subgroup is at the H mod K part, and H mod K consists of the 2 cosets. That was the 2 cosets we had previously. Yeah, H mod K consists of these 2 cosets. So we're going to take H mod K as a set consisting of these 2 elements, which are themselves sets, and to that add other sets. The other sets coming from is it G mod K? So we produce these things here. And let's look at the mapping, skipping the arithmetic. And the mapping is a little more cathartic. So the mapping, F bar, I think it was a natural isomorphism between these groups produces something like this. G mod H, the elements would be cosets of H. This is H itself. I know I got some confidence in that because it contains 0 bar, be the only one that contains the identity. That gets mapped under this isomorphism, this natural isomorphism, to this set. Well, hey, look, the things we got over here are the same things we have over here. On the left, they're in a single set, right? They're a coset of H over here. So on the left, we'll always have single sets. And on the right, we're looking at cosets. See, we're looking at cosets of H mod K. Yeah, cosets of H mod K, but it's the same elements. These are all 0 mod 4. So are these, but they're distributed somewhat differently. Here, we have a coset of H, coset of H, right? Coset of H. H mod K. So I don't have trouble intuiting this. We've got a coset of this. So I've got a little lost in the symbols. Add 1 bar to this, and that's where this comes from. And under the natural isomorphism, as I say, it's mapped to these 2 cosets, that set of cosets, and it's the same elements. Similarly, through the 4 of them here, we've got the same elements in this set as we have in these 2 sets. They're just distributed differently. Over here, all these things are congruent congruent mod 4. Over here, these are congruent mod 8, and these are congruent mod 8. So it sort of split them up, mod 4 to mod 8 in some informal sense. But there's some specific examples. Really, there's one where the theoretical results may be a little easier to follow than the examples. Let's look at these last 2 theorems and then give a little warning, and that'll take care of this section. Okay, claim here is if F mapping G into H is an epimorphism of groups, then the assignment of K to F of K defines a one-to-one correspondence between the sets S of F of G of all subgroups K of G which contain the kernel of F, and the set S of H of all subgroups of H. Under this correspondence, normal subgroups correspond to normal subgroups. First off, one-to-one correspondence is it's a bijection. They're not saying simply one-to-one when they put the hyphens in there. This is Hungerford's way. When they put the hyphens in one-to-one, one-to-one, 1-2-1 correspondence, they mean bijection. And this isn't novel to Hungerford. This is the kind of terminology you'll see elsewhere. I don't care much for it because it's too easy to confuse with the idea of a one-to-one mapping. Well, it's a one-to-one and onto mapping, a one-to-one correspondence is. We're dealing with, let's see, S sub F of G is subgroups K of G, which contain the kernel of F. Okay, that's why this is sub F. So we'll have a subfunction here, and the requirement will be that these are subgroups that contain the kernel. And S of H is simply subgroups of H. All right, so we're claiming a one-to-one correspondence between S sub F of G and S of H. All right, we started with homomorphism F. Since this is a homomorphism, K being any subgroup of G, F of K is a subgroup of H. Homomorphic images of subgroups are again subgroups. One of the exercises will establish that. We'll say in a second something about inverse images of subgroups as well. So if we take phi and define phi of K to be F of K, this is a function that maps these kinds of subgroups. There's a little bit of extra stuff going on about the contains a kernel, but more of that here after a while. They take these subgroups of G and they map them to subgroups of H by simply taking K to F of K. You know F of K is a subgroup of H by the previous line. Speaking of exercise 1.2.9, part A tells you the inverse image of a subgroup is a subgroup. Just keep an eye on where you are. F inverse image of J is a subgroup of G for every subgroup J of H. So homomorphisms map subgroups of G to subgroups of H. And when a homomorphism exists, inverse images of subgroups of H are subgroups of G. That's what the exercise deals with. Let's see, take J, a subgroup of H, that implies the kernel of F is a subgroup of the inverse image of J. Remember, J contains the identity, and the kernel is the stuff mapped to the identity. So when I take the inverse image of J, that includes the inverse image of the identity over here. The inverse image of the identity is the stuff over here mapped to the identity. The inverse image of the identity in here is a kernel of the homomorphism. So the kernel of the homomorphism is a subgroup of the inverse image of J. If we take, we started this with simply taking J to be a subgroup of H. If then you'll take F of the inverse image of J, that'll produce J itself. We started with a subgroup, took an inverse image, and then applied the function to that. I don't want to say function. This isn't exactly a composition of functions. I don't know about one-to-one. I don't know about inverse functions, but I do know about inverse images. So we took an inverse image and then applied the function and produced J in that way. J was an arbitrary subgroup of H. So we just showed phi is onto. Phi of the inverse image of J, which we know to be a subgroup of G, produces J itself. Oh, and we made the observation finally about the kernel of F being a subgroup of these inverse images. Let's see, exercise 1.5.18, the inverse image of F of K equals K itself if and only if the kernel of F is a subgroup of K. So we'll take that as given, an exercise from this section. But then we're getting, so we're mapping in the other direction here. We're getting this kind of behavior if and only if the kernel of f is less than g, and we were just using behavior similar to that. So the composition was in the other direction. But here comes a condition of requiring the kernel of f to be a subset of k. So to get this kind of behavior. By definition, S sub f of g consists exactly of all subgroups k of g for which the kernel of f is a subgroup of g. So k itself is a subgroup of g, and certainly the inverse image of f of k equals k. If k contains the kernel, then we get this kind of behavior. And so we can say, see, that was an arbitrary subgroup g of k. So the only thing mapped to f of k, and we've shown that we get these f of k's out. So I can take this and apply f to both sides, we get f of k out. The only thing mapped to f of k under phi is k itself. So we took an arbitrary, here it is, arbitrary subgroup k of g. The only thing mapped to that k, the only thing mapped to f of k is k itself. And so we've got a one-to-one function. So phi is one-to-one, it's on to, that's a one-to-one correspondence. They make an additional claim that under this correspondence, normal subgroups correspond to normal subgroups. So let's leave that as an exercise. One final result, this being a bit more tangible, this corollary seems to be the pattern in this section. If n is a normal subgroup of group G, then every subgroup G mod n is of the form K mod n, where K is a subgroup of G that contains n. A little furthermore, then we'll talk about what this means. Furthermore, K mod n is normal in G mod n if and only if K is normal in G. Okay, so we're talking about subgroups of a quotient group. What they're saying is, start with a normal subgroup, capital N, so G mod n actually makes sense, so the quotient group is defined. And they're saying subgroups of the quotient group are of the form K mod n, where K is some subgroup of G that also contains n. So they're giving you the structure of subgroups of a quotient group, and they relate, in a sense, to subgroups of the original group of a certain sort. Subgroups that contain this capital N in themselves as a subgroup. That capital N being normal in G would also be normal in K, so we don't have any concerns about K mod N. The furthermore claim, K mod N is normal in G mod N, so now they're talking about a quotient group, normal in another quotient group, if and only if K is normal in G, so it's another requirement of normality of K and G. Right? We didn't put any kind of conditions on K other than it's a subgroup of G. It contains a normal subgroup, but that doesn't mean it itself is a normal subgroup. Apparently it is, and only is when the K mod N subgroup of G mod N is a normal subgroup. Okay, consider the canonical epimorphism, mapping G to G mod N, takes element G to left coset of N in G, the left coset Gn. Kernel of that mapping is simply N itself. We've been through this a number of times. What's the identity in G mod N? It's capital N itself. So we would have elements of G mapped to left cosets of the form Gn. When does that equal N? When G is in N itself. So kernel of pi is N. We've done this several times. By theorem 11, let's see, that's the theorem we just did, right? Every subgroup M of G mod N, that is, every element of S of H, right? So we're dealing with this one-to-one correspondence stuff. S of H, here we're taking H to be the group G mod N. So here's a homomorphism, here's group G, here's group H in the notation of theorem 11. Every element M of S of H, that is S of G mod N, the M was the notation we had there. There corresponds a subgroup K of G, where K contains the kernel of the homomorphism, which we saw to be N. K is in S sub pi of G. Remember, with the G's, we had a little function, S sub F. We had a little function, homomorphism, subscript. These were, let's see, subgroups of G that contained the kernel of pi. So every subgroup M of the quotient group, there corresponds a subgroup K of G, where K contains the kernel of pi. So that was what we got out of theorem 11. The correspondence is given by, I guess we got this out of the proof. Yeah, we introduced the pi's and the mappings. We introduced the phi. Phi of K was defined to be pi of K equals M. And so pi of K, that would be under the canonical epimorphism, that'd be the K ends. The kernel of pi was N. We're taking the K's here to be from K, looking at pi of K. So left cosets of capital N, the kernel of pi, in K. And that's exactly what we got out for M. We had, well, not exactly, because we could pick up an isomorphism along the way. So we've got M isomorphic to K mod N. Oh, this is K mod N right here. I believe we got a typo there. Should we K mod N? So we got K mod N. At this point, we've got, let's see, pi of K equal to M. We've got pi of K. We probably need an isomorphic to somewhere along the lines. But this produces K mod N here. And pi of K, being both of those, produces that isomorphism between M and K mod N. Again, this M should read K mod N, not M. K mod N is normal in G mod N if and only if K is normal in G by the part of theorem 1.5.11, which states that normal subgroups correspond to normal subgroups. So we buried a little bit of that. I think we left that as an exercise. But that takes care of almost all of this section. One final comment just about the weird way quotient groups behave. A warning. The following just seems unlikely, but it's true and it's easy to find an example. It's possible to have G1, group isomorphic to group G2, H1, a normal subgroup of G1, H2, a normal subgroup of G2, and those subgroups isomorphic to each other, but the quotient group G1 mod H1 may not be isomorphic to the quotient group G2 mod H2. If you will, the numerators are isomorphic, the denominators are isomorphic, but the quotient groups are not isomorphic. An easy way to illustrate it, take the integers. Take G1 and G2 to be the integers, so we don't have just isomorphic, we got equality there. Take H1 to be twice the integers, and take H2 to be 3 times the integers. We've seen in the last section, I think it was, twice the integers, 3 times the integers, those are isomorphic to each other. In fact, they're isomorphic to the integers themselves. I can easily find a homomorphism between the integers and twice the integers as an additive group. Just take the integers and multiply all of them by 2. That's an additive group homomorphism. Or multiply them all by 3, an additive group homomorphism, isomorphism, in fact. So we get H1 and H2 are isomorphic to each other. In fact, they're isomorphic to the integers. Isomorphic to each other was what I was interested in. But then when I take the quotient groups, G1 mod H1, integers mod 2z, that's the integers mod 2. Integers mod 3z, that's the integers mod 3. It ain't isomorphic. That's got 2 elements and that's got 3 elements. So the quotient groups are not isomorphic. So this quotient group stuff may not behave in a terribly intuitive way. This just seems bizarre that we could have all these isomorphisms, yet the quotient groups are not isomorphic. So I guess the takeaway lesson is you be very careful with this quotient group stuff. You've got the isomorphism theorems that do tell you when things are isomorphic, and some things that seem really plausible turn out not to hold. And that takes care of in its entirety. Section was a 1.5. In the next section, we'll look at some specific groups. It's a lengthy section as well, but we'll look more at specific groups, dihedral groups. I don't think we've sure we formally defined those yet. We'll give certain ways to represent groups in the next section. So have a nice day. I'll see you in section 1.6.